All right, and we're back. Okay. So, if a year from now I'm watching this and I got COVID again, I know. All right. So this is section 3.6. Again, what we're doing is we're in this path of finding any sort of derivative that I could possibly get thrown at me, right? That's what we're doing here. Finding any. What's that? I mean, I don't know what we did it too late. But this section is derivatives of logarithms. Now, we're going to be doing sections 3.4 through 5 through 6, and then quizzing next week, remember. Hopefully on Wednesday, if all goes as planned on Wednesday. All right, so let's get to it. Okay, so we have not really learned the rule of derivatives of logarithms yet. I believe it is on your formula sheet. Let me take a look real quick. Derivatives of logarithms. Yep, that's down below there. You see right underneath the inverse trig function derivatives is the derivatives of logarithmic functions as well. You see also the exponential underneath there as well. We learned that a while back when we talked about the chain rule. Derivative of b to the x is b to the x ln b. And then we have derivative of log base b of x. So if you have the derivative of log base b of x, the rule is 1 over x ln b. 1 over x ln b. It's similar to the, It's similar to the exponential rule. The exponential rule was b to the x ln b. Instead of b to the x ln b, I have 1 over x ln b. So it's similar. It's really quite similar. Okay? Now, we learned that the derivative of e to the x was very simple, right? What is the derivative of e to the x? E to the x. Let's examine the derivative of natural log of x, because that ties directly into e to the x, right? E to the x, the base e, if I put a logarithm base e, that is natural log, right? That is ln. So if I apply this rule as log, that's not pen. If I apply this rule as log base e of x, this becomes now 1 over x ln of, what's my base? E. What is ln of e? What is the natural log of e? 1. So that's why it turns into 1 over x times 1, or just 1 over x. That is going to be a rule that we will use a lot. Just like we have a lot of examples that have e to the x in them, we will have a lot of examples with natural log in them. And if you have a natural log example, man, that's nice and easy, because the derivative of a natural log is 1 over x. Derivative of natural log is 1 over x. If it's a derivative of any other log, like if I have d over dx of log base 2 of x, I don't know why I would ever have a log base 2, but if I have a derivative of log base 2 of x, well, that would have just been 1 over x ln of 2. Now, remember that that's just a number, right? Please don't forget, whenever we have a natural log or a logarithm of a number, that's just a decimal, right? I could go to my calculator and do ln of 2 to figure out what that decimal would be. Yeah.
Could you think of a way to simplify that and then put it in front of the x or not?
No, because it would look like this. It would look like 1 over ln of, actually, no. It would look like this. 1 over ln of 2 times 1 over x, which that just looks weird. Yeah.
I mean, like you find the decimal value.
Yeah, I wouldn't do that. Because you're estimating it, nothing. You're finding a rounded value. So let's work with it a little bit. Let's differentiate ln of x to the third plus 1. ln of x to the third plus 1. So this is telling me that I have to do a chain rule, right? I have to do a chain rule. Why do I know that I have to do a chain rule? I've got a function within another function. I've basically got a composition. I've got x to the third plus 1 within ln of x. Okay, so that means I've got to take the derivative of ln. Well, the derivative of natural log is 1 over x. But in this case, my x is x to the third plus 1, right? Because the derivative of ln of x is 1 over x. So the derivative of x to the ln of x to the third plus 1 is 1 over x to the third plus 1. Now, I multiply by the derivative of the inside, right? Because that's what the chain rule says. Take the derivative on the outside, peel back the layer, and now take the derivative of the inside. Well, that's just 3x squared. Now I can reduce that a little bit just by putting the 3x squared on the top and keeping the x to the third plus 1 down on the bottom. Now, let me ask you this. If I take the derivative of any natural log, it's always going to be 1 over the thing inside, multiplied by the derivative of the thing inside, right? If there's a composition, if there's something inside the natural log, it will always be 1 over that something times the derivative of that something. That will always happen, right? Because it's always going to be 1 over that thing. So what I can do is kind of generalize a rule by taking this. This is what I'm going to talk through. That if you have the derivative of the ln of g of x, natural log of a function, something inside the ln of x, what you can do is just take the derivative of the inside divided by the regular inside, what it used to be. Think back to our last example. It was the derivative of the inside, that 3x squared, divided by what used to be on the inside, x to the third, was it plus 1 or something? Okay. No, you're fine. Sure. See, I keep it right here. All right, so d over dx of ln of sine of x. Okay. Do you see how I've got a function within the natural log? So my new rule tells me that I could take the derivative of the inside. What is the derivative of the inside? What is the derivative of sine? Cosine. Divided by the regular inside, right? The non-derivative inside. That's what that equals. Okay, what is cosine over sine? What is cosine over sine? Cotangent. Now, do we have to learn that rule? I mean, no. Like if I didn't use that rule and I just applied the chain rule, does that still work? Of course it does. I would take d over dx of ln of sine of x. I would just take, okay, well, the derivative of ln is 1 over that thing multiplied by the derivative of the inside. Well, the derivative of the inside was cosine x. And then I just put it on top. So I get there, and then it turns into cotangent, obviously. I get there, but if you remember the trick of, if you've got a composite function inside ln of x, if you've got a function with inside ln of x, you can just take the derivative of the inside divided by the original inside. Okay? So now, let's take the square root of ln of x. We had a function within ln, we had a function within the natural log, and now let's put a function on natural log. Let's take the square root of ln of x. So remember that is just quite simply ln of x to the 1/2 power, right? Always turn radicals into rational exponents. And now we find the derivative. So f prime of x is going to be equal to 1/2 ln of x to the negative 1/2, right? I apply, because this is going to be a chain rule, it's going to function within a function. I apply the derivative of the 1/2, bring the 1/2 down front, subtract it by 1, And now I multiply by the derivative of the inside. Well, what is the derivative of ln of x? 1 over x. And now from here, it's just reducing it. Okay, it's just reducing it. So this is really just like, okay, my 1's going to stay on top. I'm going to bring this 2 down on the bottom. I've got an x on the bottom. And do you notice how this ln of x is going to shift down to the bottom as well? Because it's a negative exponent. And so I'm going to shift it down, and as well, I'm going to take that 1/2 and turn it back into a square root. Square root of ln of x. Okay. Let's try another one. Now, is this one natural log anymore? No, this is not natural log, so I can't just make it 1 over x. I've got to go back to my rule of log base b of x is equal to 1 over x ln b. 1 over x ln b. Okay, now remember that is log base b of x. D over dx of this is 1 over x ln b. Natural log of the base. Okay, let's apply that to this. Now, if I have log base b of x is equal to 1 over x ln b, my x in this case is this whole chunk, right? Because that's what's inside the logarithm. So I take 1 over 2 plus sine x times ln b times natural log of 10. Now don't forget that natural log of 10 is just a decimal. It's just a number. Just an irrational number. Okay, that's the derivative applied to the logarithm, and now we work with the chain rule. We multiply by the derivative of the inside. We multiply by the derivative of the inside. Well, the derivative of 2 is nothing, is 0. The derivative of sine is, again, cosine. So it's times cosine x. Okay, so just putting it together. This is cosine x over 2 plus sine x ln of 10. And I believe that's all we can do. If you'd like to distribute the ln 10, then that's fine, but that doesn't really do anything. That doesn't reduce anything down. Now, can we use that same shortcut rule that we did for ln of x? Sure, but now it's no longer the derivative of the top divided by the bottom. It is now, the derivative of the inside divided by the regular inside. Now it's the derivative of the inside divided by inside times ln of the base. Okay, so it's, I don't know, in my mind, it's just easier to think about the chain rule than to try to memorize some weird trick. In my mind, it's better just to use the chain rule because I think we've kind of wrapped our arms around the chain rule a little bit. I think we know that a little bit more. So rather than trying to memorize some weird trick that only works for logarithms, let's just use the chain rule. Or maybe something like that. Maybe I'm overestimating. All right, d over dx of ln of x plus 1 over the square root of x minus 2. Let's try this one now. Again, I'm going to apply the chain rule. So what I'm going to do is first take 1 over x plus 1 over square root of x minus 2. Because that's the derivative applied to the natural log, 1 over that thing, times the derivative of the inside. Now, when I multiply the derivative of the inside, what is the inside? Yeah, isn't it a quotient? Got to use the quotient rule. It's a fraction. So again, I have to take f prime g plus g prime f all over g squared. Oh, minus, thank you. That would have stung. Minus. All right, so f prime. Well, that's nice. F prime is just 1, right? Okay, derivative of the numerator is 1 times the original g. Okay, I'll just turn that into a square root. X minus 2 minus g prime f. Okay, now, the derivative of the square root of x minus 2. Remember that this is really just x minus 2 to the 1/2 power, right? So when I go to find the derivative, that is 1/2 times x minus 2 to the negative 1/2 power. Now, we would multiply, so you got to think about this like a chain rule, where we would multiply by the derivative of the inside, because I see some sort of function on the inside. But what is the derivative of the inside? What is the derivative of x minus 2? 1. So do I even have to worry about multiplying that? No. See, when you see a chain rule that just has like an x plus or minus a number, then you don't even have to worry about it. Because in the end, it's just the constant's going to go away, so you're just going to end up multiplying by 1 anyway. Now I have to finish out my quotient rule by multiplying by f. All divided by g squared. Well, the nice thing about g squared, what's that going to turn into? Just x minus 2. Yeah. Because it would be the square root of x minus 2 squared. All right. So I'm going to turn this, because, fraction within a fraction is kind of weird. I'm going to turn this into, I'm going to flip it. I'm going to say the square root of x minus 2 over x plus 1 times, because to divide is to multiply by the reciprocal, right? Times, and now I'm going to kind of manipulate the top here. I'm just going to reduce that down a little bit. I'm going to have the square root of x minus 2 minus, okay, now watch what I'm going to do here. The x plus 1 is going to go on the top, and that's going to be divided by 2 times the radical x minus 2. Okay? The x plus 2 stayed in the top of this thing. The 2's in the bottom. This negative sign means that x minus 2 to the 1/2 kicks down, and I just turned it back into a square root. All divided by x minus 2. So now we're multiplying, so I can just multiply it in. The bottom, pretty easy, becomes x plus 1, x minus 2. And the top, well, when I distribute here, isn't that just going to give me an x minus 2? And then when I distribute here, isn't that just going to cancel my square root of x minus 2 on the bottom? So it's just going to go away. So it actually essentially just becomes x plus 1 over 2. Okay, let's just make that look a little cleaner. X minus 2. I'm going to turn this into like a minus 1/2 x plus 1. So when I distribute it in, it's going to be minus 1/2 x minus 1/2. All still divided by the x plus 1, x minus 2. And that gives me 1x minus 1/2 x is positive 1/2 x. And then a negative 2 minus 1/2. So that's like negative 2.5, right? Turn that into a plus. Oh, I screwed up on my thing. That should be a minus. I wrote a plus here. That's not good. I forgot to distribute in the negative. So it's 1/2 x minus 2.5, or which would be 5/2 if I'm looking at it as a fraction. If you wrote 2.5, that would be totally fine. And that's about as clean as we can get it. Yeah.
Could you just leave it as x minus 2 minus x plus 1 over 2? Or...
Yeah, honestly, that I didn't really do much. The only thing is I could have combined like terms.
Yeah.
That's why I'm putting it together.
Okay.
Yeah. I got to be honest. On your tests and quizzes, I'm really lenient about where you stop. And here's the reason. I don't know, maybe other teachers would disagree with me, but like, what's the calculus part about this? I mean, the calculus part about this stops right here, right? And that's really what I'm trying to get you to learn. Like, this on is like algebra, right? This is just manipulating a function, manipulating a fraction. So I'm really lenient once you get beyond the calculus. If you make a good train of thought and try to reduce as much as possible, then I'm usually okay with it. Okay. Let's take a look at one more example here. So find f prime if f of x is equal to ln of the absolute value of x. Okay, well, let's try to take this piece by piece, right? So if I'm taking d over dx of ln of x, or ln of absolute value of x, excuse me, I apply the chain rule because this is the absolute value function within the natural log, right? Okay, so let's apply the chain rule. This would be 1 over the absolute value of x times, well, what is the derivative of the absolute value of x? That's what we're going to examine here in a second. This is really what I need to take next, right? Because it's the derivative of the inside. I'm applying the chain rule, but remember that the derivative of the absolute value is weird. You know, think about the equation. Think about the graph. Think about the slope on that. It changes. It's all dependent upon whether x is negative or positive, right? And just as a reminder, what's happening at 0? It's a corner point, right? It's a kink, as the book would call it, right? Is it differentiable at 0? No. Okay? So remember that the absolute value, the derivative of the absolute value of x is a little weird. It's got two different spots. So let's redefine that for ourselves. D over dx of the absolute value of x has two pieces there. It's 1 if x is greater than 0. It's -1 if x is less than 0. Right? It's the opposite. It's that -1 value if x is less than 0. I can see that just by looking at the slopes on either side of the 0 there. So that means this whole function, f prime of x, is also defined in two separate ways. Okay? You got to think about this. Okay, if x is greater than 0. Well, what's happening if x is greater than 0? What does 1 over the absolute value of x become if x is positive? Just 1 over x, right? Because if x is a positive number, then it's just 1 over x. Okay. What is the derivative of the absolute value of x if x is greater than 0? 1. So I could write a little times 1 if I really wanted to, but I don't need to if x is greater than 0. Well, the other option is when x is less than 0. Okay, if x is less than 0, what does this become now? Oh, that's 1 over negative x, right? It's the opposite of x. Like if it was -5, I would have to say -5 to turn it back positive, right? You'd have to say the opposite of that number to get it to turn positive. Okay, so there I evaluated this piece when x is less than 0. What is the value of this when x is less than 0? -1. Well, what am I doing with those two negatives? What happens? They cancel. So this actually happens to be, let me write it out one more time to kind of simplify it a little bit. 1 over x if x is greater than 0, or 1 over x if x is less than 0. So what can we say then? Well, that means f prime total is just 1 over x, provided where x is non-zero. Okay. As long as x is non-zero, then this actually just evaluates all the way down to just 1 over x. And the reason is because it's absolute value. It's because it's two different things. It depends on whether x is greater than 0 or whether x is less than 0. All right, I'll stop there for today. I'm seeing some kind of glazed over looks. So I'll stop there for today.